Hey everybody, so today we will discuss about lesson 7, the last lesson for unit 4. Uh, we have here the topic rank, nullity, and fundamental matrix spaces. In the last lesson or previous discussion, we investigate the relationships between a system of linear equations and the row space, column space, and null space of its coefficient matrix. So in this particular lesson, we will be concerned with the dimensions of those spaces. The results we obtain will provide a deeper insight into the relationship between a linear system and its coefficient matrix. So we have here the row and column spaces have equal dimensions. For example, we have here matrix A with this set of coefficient values, in which this size of this matrix is a 4 by 6 matrix. Both have 3 basis vectors and hence both 3-dimensional. The fact that these spaces have the same dimension is not accidental, but rather a consequence of the following theorem. So the theorem states that the row space and the column space of a matrix A have the same dimension, which means that each row and column space should have the same dimension. Rank and nullity. The dimensions of the row space, column space, and null space of a matrix are such important numbers that there is some notation and terminology associated with them. So the proof of this shows in a theorem, or theorem 4.9.1 shows that the rank of A can be interpreted as the number of leading ones in any row echelon form of A. By definition, the common dimension of the row space and column space of a matrix A is called the rank of A, and it is denoted by rank A. The dimension of the null space of A is called the nullity of A, and is denoted by nullity A. For example, rank and nullity of a 4 by 6 matrix. Find the rank and the nullity of the matrix. Solution. The reduced row echelon form of matrix A is the following. So you could also verify this solution on your own. However, but you will arrive on the same notation as this one. So you could see that the 2-row echelon form are non-zero. Most of it are non-zero numbers, while the 3rd and 4th rows are 0 numbers. Since you could see in this matrix has 2 leading ones on its row, you could see here, and column spaces are 2-dimensional. You could say, or you could conclude, that the rank of A is equal to 2, since you base it on the 2 leading ones. To find the nullity of A, we must find the dimension of the solution space of the linear system AX is equal to 0. So this system can be solved by reducing its augmented matrix to reduced row echelon form. The resulting matrix will be identical to the equation 1 or to the matrix 1, except that it will have an additional last column of zeros, and hence the corresponding system of equations will be x sub 1 minus 4x sub 3 minus 28x sub 4 minus 37x sub 5 plus 13x sub x 6 is equal to 0. We have also x sub 2 minus 2x sub 3 minus 12x sub 4 minus 16x sub 5 plus 5x sub 6 is equal to 0. Solving these equations for the leading variables, it could yield on the following equations, from which we obtain the general solution. You could see here the general solution of x sub 1 is equal to 4r plus 28s plus 37t minus 13u, and x sub 2 is equal to 2r plus 12s plus 16t minus 5u. X sub 3 is equal to r, x sub 4 is equal to s, x sub 5 is equal to t, and x sub 6 is equal to u. Or in column vector form, we could have these sets of vectors x sub 1 to x sub 6, wherein it is equal to r, and the set of 4 2 1 0 0 0 plus s, and the set of 28 12 0 1 0 0 plus t 37 16 0 0 1 0 plus u with a set negative 13 minus 5 0 0 0 1. Because the 4 vectors on the right side of the formula form a basis for the solution space, and it follows that the nullity of A is equal to 4. Take note again, because the 4 vectors on the right side of the formula form a basis for the solution space, means there are 4 bases which also equivalent to 4 nullity. Example number 2, maximum value for rank. What is the maximum value for rank? Possible rank of an m by n matrix A that is not square. Solution: since the row vectors of A lie in Rn and the column vectors in Rm, the row space of A is at most n-dimensional and the column space is at most m-dimensional. Since the rank of A is the common dimension of its row and column space, it follows that the rank is at most the smaller of m and n. We denote this by writing rank of A is less than or equal to the minimum of mn, in which the minimum mn is the minimum of n and m. Okay, so whatever the value is there. Next, we have here the dimension theorem for matrices. States that if A is a matrix with n columns, then rank of A plus nullity A is equal to n. For example, the sum of rank and nullity. The matrix A has 6 columns, so rank of A plus nullity of A is equal to 6. This is consistent with example 1, where we showed that rank of A is equal to 2 and the nullity of A is equal to 4, wherein you will add this 2 is equal to 6. Theorem 4.9.3 states that if A is an m by n matrix, then rank of A is equal to the number of leading variables in the general solution of AX is equal to 0, and B is nullity is of A, the number of parameters in the general solution of AX is equal to 0. For example, we have here the rank, nullity, and linear systems. First, find the number of parameters in the general solution of AX is equal to 0 if A is a 5 by 7 matrix of rank 3, and B is find the rank of a 5 by 7 matrix of A for which AX is equal to 0 has a two-dimensional solution space. Solution A, from equation 4, the nullity is equal to of A is equal to n minus the rank of A. So 7 minus 3 is equal to 4, wherein you could say that there are 4 parameters. So the nullity of A is equal to 4. The matrix of A has nullity for solution B, wherein the matrix of A has the nullity of 2, since you have two-dimensional solution space. So rank of A is equal to n minus the nullity of A. 7 minus 2 is equal to 5. So the value of the rank of A is equal to 5. Recall also from section 4.8 or in the previous section that if AX is equal to B is a consistent linear system, then its general solution can be expressed as a sum of the particular solution of the system, and the general solution of AX is equal to 0. We leave it here, okay, for you to prove. However, theorem 4.9.4 states that if AX is equal to B and it is consistent linear system of m equations in n unknowns, and if A has rank R, then the general solution of the system contains n minus R parameters. So we have here the fundamental spaces of a matrix. There are 6 important vector spaces associated with an m by n matrix of A and its transpose AT. So we have here row space of A and the row space of the transpose of A. However, transposing a matrix converts the row vectors into column vectors and conversely. So except for a difference in notation, the row space of AT is the same as a column space of A, and the column space of AT is the same as the row space of A. Thus, of the 6 spaces listed above, only the following 4 are distinct: row space of A, column space of A, we have the null space of A, the null space of AT. These are called the fundamental spaces of the matrix A. The row space and the null space of A are subspaces of Rn, whereas the column space of A and the null space of AT are subspaces of Rm. The null space of AT is called the left null space of A because transposing both sides of the equation ATX is equal to 0 produces the equation XTA is equal to 0t, in which the unknown is on the left. The dimension of the left null space of A is called the left nullity of A. We will now consider how the 4 fundamental spaces are related. Let us now focus for a moment on the matrix AT, since the row space and column space of a matrix have the same dimension, and since transposing a matrix converts its columns to rows and its rows to columns, the following results should not be surprising. So in the theorem 4.9.5 states that If A is any matrix, then rank of A is equal to rank of AT. So we have here also the basis for the fundamental spaces. An efficient way to obtain basis for the 4 fundamental spaces of an m by n matrix A is adjoined to the m by n identity matrix to A to obtain an augmented matrix, and apply elementary row operations to this matrix to put A in reduced row echelon form R, thereby putting the augmented matrix in the form RE. In the case where A is invertible, the matrix E will be A inversed. So we have here the nullity of AT is equal to M minus R. That follows from the equation 5. Basis for the 3 of the fundamental spaces can be obtained directly from RE as follows. A basis for row of A will be the row R rows of R that contain the leading ones, which is the pivot rows. The basis for column A will be the R columns of A that contain the leading ones of R, the pivot columns. The basis for null of AT will be the bottom M minus R rows of E, and see the proof at the end of the section also. So we have here the example 5, the basis for the fundamental spaces of 4 by 6. So you could see here the matrix and the identity, the coefficient matrix and the identity matrix. And we have here the R, or the reduced row echelon form, and the equivalent matrix. We have here the row basis, the column basis, and the left null basis. So I think that's all. Thank you so much for listening.